This approach to potentials, to understanding potentials in terms of spherical harmonics, leads to an additional tool that we can have, and that is used frequently, in particular in particle physics, and actually also in astrophysics. Where if I've got some distribution of something, let me, because this is electromagnetism, say I've got a distribution of charge. That's a bird. Distribution of charge. Right. Over here. But I actually can't get close to that over there in order to do a specific set of measurements of where the charge is. Right? But I'm only able to access some region, or rather outside some region around the charge, right? And maybe I'm only looking at it from really far away. So I'm over here, and I'm looking at that over there. And trying to figure out, saying, well, what do I know about that charge distribution over there, right? One thing I would know right off the bat is if I didn't count up, but if I have an unequal number of plus and minus charges, there'll be net charge, right? And if there's net charge, then out here, the potential is going to drop off as 1 over r. The net charge, actually Q net over r. But wait, there's more. If I'm out here and I'm inspecting that over there, I can learn more. If the charge distribution over there is a dipole charge distribution, so net charge is 0, that means that this term is going to go to 0 if it's a dipole. When we go through and solve for the angular dependence and the distance dependence of the potential, we'll find that there is a specific angular dependence and a specific distance dependence. It's going to look like 1 over r squared for the potential for a dipole. If the charge has some other distribution, maybe it's got some additional symmetry to it. It's the charges sitting, equal and opposite charges are sitting on corners of a cube. Then it will turn out that the potential at greater distance will fall off in a different way and have a specific angular form. The charge on the corners of a cube will actually turn out that potential out at distance has a behavior we call octupolar behavior, right? So what we could do experimentally then, so we can't access, let's say that's a nucleus over there. We can't get into the chicken coop. We can't actually access that, but we can measure at a distance. Maybe we can scatter things off of the potential. Maybe we can pass things through the potential or through the field, and as a result, they will take a certain trajectory. And based upon that, we can get an idea of the angle and distance dependence of the potential and or the fields, right? Then based upon that, we can work our way back and say, oh, here's one of the properties of this charge distribution that we didn't know before, that we have learned about, this charge or mass distribution that we didn't know before, that we can learn about from gravitational effects or effect of light passing through a region that has stars in it, for example. All right. So as long as I can have some region here in which the charge is confined, then when I get far enough away, well actually, when I get outside of that region at all, right, not just far enough away, the potential is going to be the sum over all possible solutions, L m equals minus L plus L. I don't know whether I wrote that down or no. 2L plus 1. Q sub Lm, that's a coefficient. Y Lm. Yeah. R to the L plus 1, right? The potential is going to look like this outside of that region, right? But if I get far enough away, there will always be a lowest order term in R that's going to dominate potential. So I've got this whole sum here, but whatever the lowest order term is, lowest meaning the smallest L, is the one that when I get far enough away, that's all that's going to be left. Because all the other terms, no matter what the coefficients are going to drop off faster than our 1 over R, right? So if there's net charge, then I'm only going to have the 1 over R term when I get far enough away. So that immediately tells me there's net charge there, okay? Potential will be dominated by that. If it's a dipole, we'll work this one through. It'll turn out that there's a 1 over R squared term here. And I'll have harmonics that will also confirm the direction which the dipole points, right? I want to find out what these coefficients are. And these coefficients depend upon the charge distribution that I actually have over there. So the QLMs are that's a volume integral, but I'm not going to write it all out. Oh, let me write it as X, because this is radial, and this is the actual position. Primed meaning the positions of the charge. That's charge density. That's volume. So I'm using the orthogonality properties of the spherical harmonics. Okay. And I'm integrating over the charge density itself, where the charge is. And that will tell me what the coefficients for the various terms are. Yes?
What's Y sum?
What's what?
What's,
It's the complex conjugate of the spherical harmonics. And spherical harmonics just got an e to the I and phi in it.
right.
So you just need e to the minus I and phi. That's basically it. Everything else is real in the spherical harmonic. Okay, so if I knew the charge distribution, then I could figure out what terms are going to dominate the potential that I see far away. But most of the time you don't actually know the charge distribution, so you invert the problem and you measure the potential far away and try to figure out what the charge distribution must have been. And again, if you have a dominant term in the potential far away, then you know that that's the lowest order of Q that is not zero. Okay, so let's see. I have the dipole here. What do I want to say about the dipole? I haven't told you what a dipole is yet, have I?
Nope. That would be kind of useful.
Yeah, okay. So I guess we'll do that first.
Not all of us are star students like you.
But this is the idea. Now let's see what the potential looks like for various specific charge distributions.
Star student.
So a dipole are two equal and opposite charges that would be placed a distance d apart, right? But I can play with the strength of the charges and the distance d, so that if I wanted to make these two charges really, really close together, I could increase the strength of the charge, the magnitude of the charges, so as to keep the product q times d a constant. And we define that as the dipole moment. So I can keep d fixed and go very, very far away, and that's what I'm going to do here, all right? Or I could consider d to shrink while I sit at a reasonable distance, just allow d to get smaller and smaller, all right? So this is more justification for where everything's going to come from. I want to solve for what the potential of this looks like. So I can write that v of r is going to be equal to plus q over the distance to the positive charge minus q over the distance to the negative charge, right? So I would go out to some point here. Those are straight lines. And work out what those distances are. I know the distance from here to there, and this is going to be a little bit shorter, and this is going to be a little bit greater. So if this distance at the center is r, and this angle here is, I'm just using this to start out with, then we're going to reduce it. But I'm going to write it as theta. Okay? So this angle is theta. Then I can work out what those distances are. I can use the log cosine and end up with r plus squared equals r squared plus 2 squared minus r d cos theta, which is approximately equal to r squared times 1 minus and I could do the same thing for the negative charge. But what I want is the difference between the two of them. Right? And using that as my approximate expression, the 1 over r plus minus 1 over r minus is approximately equal to d over r cosine theta. Where I've dropped off terms in d over r squared, right? So I've had to say I'm far enough away that I can use the first one. And it's actually not an expansion, I'm just squaring things out and then ask which terms survive, which ones drop the least slowly. So I end up then with v of r is equal to q d over r cosine theta, which is, now, I erased them over here. Maybe I never wrote them down. I can look at what the spherical harmonics look like and then ask, okay, well, what does that look like in terms of spherical harmonics? I could figure that out without working, without having to remember anything, by just multiplying both sides by the sum of the spherical harmonics and find out which terms survive, right? But this I can rewrite as q d. I dropped something here. Yes. Back here, r squared.
It's because you're
It's
supposed
just
to have a
d
square
over
root.
r squared. What?
You're supposed to have a square root.
No. Because you need to
It
keep
comes
in.
from, this is right. Yeah, I'm just expressing r plus squared here. Sorry. Yeah, then I actually skipped a step here thinking that I didn't need to show it to you. And so I guess I actually should show it to you. And I'll just write it down here. Oh, wait. It's easy.
He's invoking mathematics.
Yeah, I'm just waving my hands and telling you that it's easy. But I can say that if r plus is that, using the law of cosines, then 1 over r plus is 1 over r times 1 minus d over r cos theta. And 1 over r minus is 1 over r times 1 plus
What the fuck?
cos theta. And now I'm going to take the difference between the two, which is going to cancel this term out, and leave me with the d over r squared term. Okay? But I already eliminated one term here. There were higher order terms. I already eliminated one, and so this is an approximation. But if I get far enough away and d is much greater, oh sorry, r is much greater than d, then that's a good approximation. All right. So now I can come back here and write this supposed to be d over r squared. Yes. y10, and then I need to normalize it because I put the y10 in there. Square root of 4 pi over square root of 3. That's it. Okay? So I've got a constant times the y10 spherical harmonic. Right? Why is it y10 here? Actually, the reason it turned out to be y10 was because of the way that I chose my axes here, and I said I'm going to measure theta that way. All right? And I am first of all, the 0 comes from the fact that this problem has azimuthal symmetry. But we just solved the problem. We just wrote it down and we solved the problem. Okay. But the 0 comes from the azimuthal symmetry, and it ends up showing up here. The fact that it's azimuthally symmetric shows up there in the 0. Okay. And the 1 says that it's the first order solution. Okay. Or realizing that QD, I've been told that I shouldn't erase and rewrite because people are having trouble keeping up with me. So I'll rewrite that as P over R squared, Y10. Now I don't have to sneeze. Y10 square root of 4 pi over 3 P over R squared. That's it. This is the dipole moment. Now, this thing is what we call the dipole moment. Dipole moment has a direction. So what I should really do is put a direction on P and a direction on D, which is the vector pointing from the plus charge to the minus charge. But the potential doesn't have direction, so I'm okay there. Now I've got the potential. The electric field is minus the gradient of the potential. And I'll do it in spherical coordinates. E sub r is 2p cos theta over r cubed. So the field drops off as 1 over r cubed. There is a theta dependence. Is the derivative I'm taking is minus 1 over r d phi d theta, and that's equal to p sine theta over r cubed. And e sub phi, we already know what that is. So we can go ahead and take the derivatives, is minus 1 over r sine theta d phi d potential d angle is 0 because it's azimuthally symmetric, constant. Okay? What that tells us the field looks like is actually just what you knew the field looked like. When we get out into this region here, up close it's not so easy. But out far enough, it basically looks like and I guess I screwed up with my definition of theta because it appears as though theta must be measured from here. Theta. And then the field in this direction is, did I do that right? Yeah, no. I had my theta right. Never mind. Okay. So I have my components of the field. I've got my radial component and my angular component at each point here. And that tells me what the strength of the field looks like. Yes?
Are those all being rescaled by the normalization constant? Or drop out?
Yes.
Normalization
Well,
constant comes
okay.
in when you use.
I don't actually have to do that. If I used spherical harmonics, then I need all of that. But because the potential actually looked like that, I mean, I wrote it in terms of spherical harmonics in order to remind you that it could be expressed as a spherical harmonic. But the actual potential is this, and that's what I took the derivatives of. Okay. Did that. Okay, that's the first order term. But what about the justification for the multipole expansion, for the full multipole expansion? And I did that just for a dipole. What if I have a distribution of charges there?
Can you pause for a sec so I can switch over to memory
Yes,
card?
well, I'll erase while you